Welcome. We're going to take a look at limiting reactants. So whether you were in class and just want a refresher on how this works, or maybe you missed class and want to learn what limiting reactants are, this video is for you. So limiting reactants, if we have a chemical reaction, the reaction itself is going to stop when we run out of one of our reactants. So let's say a chemical reaction is taking place, A plus B, and it's turning into AB. If we've got a certain amount of A and a certain amount of B, and let's say B runs out, okay, that means even though we've got plenty of A, we've got A left over, there's not enough B to produce any more AB, so the reaction will just stop. Another way to think about this is, let's say you have hamburger patties and you have buns. That makes, you got it, a hamburger. That's a pretty good hamburger drawing too, if I do say so myself. So if we have, we'll say 10 hamburger patties and 5 buns. Well, what's going to happen then is we're going to run out of hamburger buns before we run out of patties. And so in the end, even though we've got plenty of patties right here, the most that we can make from hamburgers is going to be 5. And that's because our limiting reactant is going to be this guy right here, our hamburger buns. It's going to stop us from making any more hamburgers. Let's see, a limiting reactant limits the extent of the reaction, so it determines the amount of product that has formed our theoretical yield. It's the one that runs out first. So it's going to be like the buns. It's the guy that we run out of, and it's going to determine how much we can actually make. And that theoretical yield, where that's going to come in handy then, is when we do percent yield problems, which are actual over theoretical. We're going to toss that theoretical yield in there. And whatever we have left over, that would be our excess reactant. So the one that we run out of is our limiting reactant, but the one that we have extra of, the other guy, would be our excess. So we have an excess of hamburgers in that last problem, or that example. All right, so you're looking at a problem on a test or on a worksheet, and you're trying to decide, all right, is this a limiting reactant problem or just a general stoichiometry problem? The way you identify a limiting reactant problem is that you will be given 2 variables. That's right, 2 variables. So with a normal stoichiometry problem, you would just be given one given. All right, so you've got 15 grams of sodium carbonate. How many grams of sodium chloride will you produce? With a limiting reactant problem, you'll see 2 different givens. So you've got 15 grams of sodium carbonate and 3 grams of hydrochloric acid. How much sodium chloride would you produce? With 2 things like that, that means you're going to have to produce or do 2 separate stoichiometry problems. So all limiting reactant problems really are is just 2 stoichiometry problems in one. So you'll do 2 grams to moles, eventually to gram conversions. All right, here are these steps for calculating out the theoretical yield. Step number 1 is to identify both ingredients, which are the givens. All right, the givens, those are the ones that we just talked about, so the 2 ingredients. When you see those, do yourself a favor and underline them. So underline the 2 givens. Next, start with the given number and go to moles of desired product. So given number 1, we've got those 2 givens. Start with the first given, do stoichiometry, and calculate the moles. Make note when we do this, we're just going to moles. So given number 1 is probably going to be in grams. So you would go from grams to moles, just to moles. So you're not going to go all the way to grams yet. Next, you're going to do the exact same thing with given number 2. All right, so given number 2, do the stoichiometry, grams to moles, and you're going to stop at moles. What you're going to have then is 2 numbers of moles of the same product, and you're going to compare those 2 numbers. So you can't produce both of those. One of them is going to limit your reactant, and it's going to be the one that forms less moles. So you've got these 2 numbers right here. Both of them are moles of the same product. The one of those 2 that is smaller is going to be your limiting reactant, and that's going to decide how much you can make. You can't make any more than that, so the other number is going to be irrelevant. And then so in step number 5, take whichever one of these 2 numbers is smaller and convert it to grams. So up here we're going grams to moles to moles. In this last step, you're going to take whichever one of those is smaller and bring it all the way to the end to grams. All right, here's a practice problem for this. So we have this reaction right here. This is phosphorus, P4, reacting with oxygen gas to produce P4H10. So this is a balanced reaction already, so we can go right to our equations. So let's take a look at our steps one more time real quick. First step is to identify both of those ingredients. Then we're going to do the stoichiometry with given 1, then with given 2. Look for the one that's less moles, and then convert the less moles into grams. All right, so like I said, you want to go ahead and underline your ingredients. So in this case, we have 25.4 grams of phosphorus and 50 grams of O2. Those are our two givens. Those are the two numbers that we're going to do stoichiometry with. And we need to convert them to a product, and so the product we're looking at is P4HO10. Okay, so that's step number 1. We've identified everything. Let's do step number 2, which is to convert given number 1. And given number 1 is 25.4 grams of P4. And we're going to convert that into moles of P4H10. So let's remember grams to moles to moles to grams. And remember, for the step numbers 1 through 3, we're just going from grams to moles to moles. We're going to stop there. So 25.4 grams of P4. The molar mass of P4 is 124.0 grams of P4. That's 1 mole of P4. So that gets rid of grams. We're now at moles. We're going to go one more step to get over to moles of our product, which is P4H10. So if we look up at our balanced equation, there's 1 mole of P4, 1 mole P4, for every 1 mole of P4H10O10, 1 mole P4O10. Moles cancels out moles, and we can solve this one now. So when we type that into our calculators, we find out that it's 0.205 moles of P4O10. All right, so that's just step number 2. We figured out, okay, if we've got 25.4 grams of phosphorus, here's how much P4O10 we could produce in theory. We've got to look at this other ingredient, though, to see whether or not that's the correct amount. So we've got 50 grams of O2. 1 mole of O2 is 32 grams of O2. Grams cancels out grams. Now, in this case, it's still 1 mole of P4O10. But if we look up at our balanced equation, there's 5 moles of O2 for every 1 P4O10. So that means we'd put 5 moles of O2 here. See, and moles cancels out moles, and then when we calculate this out, we get 0.313 moles of P4O10. So then we need to compare these two numbers, so 0.205 and 0.313. So with 50 grams of O2, we could produce 0.313 moles of P4O10, and with 25.4 grams of phosphorus, we could make 0.205. So the deal is then, if we can only produce 0.205 with this guy, that means he will be our limiting reactant, and that's how much we can produce, the smaller number. So we're going to run out of phosphorus before we can get all the way up to 0.313. So this number is useless to us. All right, we've got that number. That's our limiting reactant. That's how much we can actually produce, how many moles. This is where we now do step number 5, which is to convert this into grams. So we're going to take up here on our little chart, we're going to now go over to gram island. So go ahead and close up that by using the 0.205. Let me clear my screen. So we're going to produce 0.205 moles of P4O10 and 1 mole of P4O10 is 284.0 grams of P4O10. Those two cancel each other out, and so when we solve that, we would see that we would form 58.2 grams of P4O10. So that then would be our theoretical yield of P4O10. With those two ingredients, we're going to have extra oxygen, and we'll produce, in the end, 58.2 grams. Okay, here's three other questions you're going to run into when you do these kind of problems. What was the limiting reactant? So what formula, what compound was it that ran out first? What was the excess reactant? And then the third question, how much excess do we have left over after the reaction was complete? So for the limiting reactant, this is the compound that ran out first. This is the one that decided how much we could make, the guy who stopped the reaction. So if we think of our example, the limiting reactant there would have been the P4. Oops. Because we ran out of P4 before we ran out of oxygen, so it limited our reaction. So then the one in excess, that's the one that we had extra of, and we had extra O2. So then this third question, this one's a little more complicated. How much excess did we have left over after the reaction was complete? So we've already said there's going to be extra oxygen. Well, the question is, how much extra oxygen? After this reaction is complete, how much oxygen will be left inside of our reaction vessel? So to do that, that's a little trickier of a calculation, and there's a few more steps to figure that out. And the steps to calculate out the excess are as follows. Step number 1, convert the moles of product formed from the limiting reaction back to the grams of excess reactant to find out how many grams were needed. So if we think back to the steps for calculating limiting reactants, this would be what we calculate in step number 4. So the one that's less, we're going to take that number of moles and we're going to convert it back to the excess reactant to find out how many grams were needed. That's going to give us how many grams we really should have had. So their excess reactant, how much was actually used. We can take that number and subtract it from how many grams we had, so how much we started with, and that'll tell us how many grams were left over. Okay, so just remember those two steps, and we'll practice this with the same example. So still dealing with the same amounts of P4O2. We have 25.4 and 50 grams. Question now is, how much excess did we have left? So our excess was oxygen. We're going to have extra oxygen left inside of our flask. Step number 1 for calculating the excess was to convert the moles formed from the limiting reactant back to excess. So from step number 4, that number was 0.205 moles. So we already decided we can only produce 0.205 moles of P4O10. So we're going to convert that back to the excess, and the excess is O2. So there was 1 mole of P4O10 for every 5 moles of O2. And 1 mole of O2 is 32 grams. What this means then, in order to produce 0.205 moles of P4O10, which is what was produced, we would need to use 32.8 grams of oxygen. So we had 50. This is what we threw inside of our flask when the reaction started, but we only used up 32.8 to produce this many moles of P4O10. So then how much will we have left over? So if we started with 50 grams and we used up 32.8 grams, that means in the end we would have 17.2 grams of excess O2. So yeah, 17.2 grams of oxygen left over. Alright, so those are the steps. There's some other practice problems here on the website with videos, so you can give some of those a shot. Go back to this video if you need to check over the notes again, or if you have any questions, you can see me in class.